Hi, in this second set of slides devoted to LISA, local spatial autocorrelation, we'll talk about two other local spatial autocorrelation statistics. So far I've covered the local Moran. Now I'll cover the local Geary, which is a LISA statistic in the strict sense, and then the Getis-Ord Statistics, which are local statistics but not pure LISAs in the strict sense. So local Geary, we've seen in the previous module, global Geary is a statistic that is very similar in structure to the local Moran, except instead of a similarity measure based on cross product, which is the case with the local Moran, it's based on square distances. So numerator, again, if we look carefully, we have the double sum over I and then over j. So naturally, this part will be the component that makes up the local statistic. And there's actually two versions of this that I looked at when I initially developed this. One has a scaling factor, but as it turns out in practice, that's irrelevant. So this is the easiest way to think about the local Geary statistic. So it's a difference, square difference between the values at pairs of observations that are neighbors of I. So we're looking at I, a given location, and then for each of its neighbors, only those wij that are actually not zero, we count the square difference in the attributes. So very simple. Once you get the knack of it, anytime you see a statistic with a double sum like this, then you know the second part will be the local part. As I mentioned, for the local Moran, we can compute what the moments are under different assumptions, and these moments are when the statistic is when the weights are row standardized and the variable is standardized itself. It's very strange. The mean of the local Geary statistic is 2. So that's something that is can be very confusing, and instead, as before, I tend to use and favor very much the use of a conditional permutation. Same principle, you hold the value at the location fixed and you shuffle everything around and compute your reference distribution. So, what does this local Geary actually do? It's kind of interesting because it's a different criterion of attribute similarity. So the local Moran is related to cross-product logic, which is related to a notion of a regression fit and a regression slope. Geary C doesn't have that. It's very different. It's about difference in a way. It's about the distance, or technically square distance, in attribute space. So in attribute space, we can think of our point on a line. We have x at I and then x at j. What is the difference between these two? And then more specifically, we look at the weighted average of these attribute distances to the neighbors only. And is this distance, so think about what we're measuring here, square difference. So if the neighbors are very similar, these square differences or square distances will be very small. If the neighbors are very dissimilar, negative spatial autocorrelation, these ones will tend to be larger. So the whole point is we compute the average of the square differences with the neighbors and then compare the particular value to what we would obtain under a reference distribution of spatial randomness. It's the same principle. It's very easy to implement once we go back to this fundamental notion of spatial randomness. You just reshuffle. But it's important to note the distinction between the Moran Xi and the Geary C. Geary C is much more in a similar logic as the variogram notion in geostatistics I referred to before. Moran Xi is very much like a Pearson correlation coefficient. So it's a natural, intuitive notion of correlation, Geary C is not. It's not about correlation at all. It's about distance in attribute space. So how do we assess, once we have established that a location is significant? Remember, for Geary C, the global Geary C, the mean was 1, and values less than 1 were positive autocorrelation, and values larger than 1 were negative spatial autocorrelation. It's the same thing here. If the value that we observe at a location is less than the mean of the reference distribution, then that suggests similarity or positive spatial autocorrelation. If the value is larger than the mean, that suggests dissimilarity and negative spatial autocorrelation. So just like the interpretation of the global Geary C, it's the opposite of the sign in a sense, because it's measuring dissimilarity. So small is positive, large is negative. So in the local Moran, we, as I mentioned, cheat a little bit in that we take the significant locations and then match them with the 4 quadrants of the Moran scatter plot to interpret the type of association. With Geary C, in a strict sense, we can't do this because there is no such thing as a corresponding scatter plot with the 4 quadrants. So what we do is instead is we see the extent to which we can interpret these clusters using the same logic as the Moran scatter plot, but it's not perfect. I mean, we could be lucky and find out that the positive local spatial autocorrelation, so those locations that are more similar to their neighbors than would be the case randomly, these could correspond to either high-high or low-low quadrant points, but they could also not. And so what we've implemented in GeoDa is an initial check. If we can classify them as high-high and low-low, we show them as such. If we cannot, we show them as other because we don't know exactly what it is. See, this may seem a little counterintuitive, but the Moran scatter plot is really based on a notion of correlation, on a notion of cross product. And here, we're not dealing with that. We're just dealing with distances. So we're dealing with distances and how these distances somehow stack up to each other. And then with negative spatial autocorrelation or dissimilarity, we're totally out of luck. And think about this for a second. With a square difference, the sign is gone. So we don't know whether xi is actually larger than xj or xj is larger than xi. All we know is that the difference between them, in a squared sense, is larger than it would be under spatial randomness. So the negative spatial autocorrelation or the dissimilarity indication in the local Geary could be either high-low or low-high. We have no way of telling. That's a major difference with the local Moran. But other than that, it's the same principle. You know, it's a global statistic, which is a sum over I of these components. The component becomes the local statistic. We compute significance using conditional permutation. And then we see what we can do in terms of interpretation. If we're lucky, we can interpret it. If we're not, we have to classify as other. So here, this is still using the donation example. These are our significant locations. These are the ones that are significant and happen to fall in the high-high quadrant for the Moran scatter plot. So these we can classify as high-high. Then these other ones here, all of these, they happen to fall in the lower quadrant here, in the low-low quadrant. So now we're in business and we can classify them as low-low in the cluster map. As it happens in this particular example, we do not have cases where positive spatial autocorrelation cannot be classified. So remember, positive spatial autocorrelation for Geary C is a small value, smaller than the mean of the reference distribution. So with that small value in hand, we can assess whether this is significant or not. For the significant locations, we can assess where they fall in the Moran scatter plot. In this particular example, they very nicely fall in high, high, and low, low, but that's often not the case. And then finally, the negative spatial autocorrelation, that just says that a location is very dissimilar from its neighbor in a sense of averaging the squared distances in attribute space to those neighbors. And here we have two locations, one of which is actually in the high quadrant. So for negative spatial autocorrelation, the interpretation in terms of high-low and low-high is not that easy. And it's actually a little more complicated than for the local Moran. In the local Moran, typically, it will be very unusual to get spatial outliers next to each other, but with the local Geary, that tends to be more common. So it's a different thing. It's a different notion. It focuses on the comparison of distance in attribute space to the comparison to the distance in geographical space. We saw this in our smooth distance scatter plot before. It's the same logic. We'll encounter this logic again later when we move to the multivariate domain, and also when we investigate clustering in general, which I do in the spring course. So just like with Moran's eye, we can make a significance map for different p-values, and as we crank up the p-value, so to speak, the map shrinks and focuses on really interesting locations. In this case, we find locations of positive spatial autocorrelation at the low end here and at the high end there. How does this compare to local Moran? They're different animals, they're different things. They measure they use a different criterion to measure attribute similarity. So a priori, there is no reason why they would give the same result. If they do give the same result, that gives us more confidence that something interesting is happening in that location. If they don't give us the same result, then that should make us think about what each of these evaluation criteria for attribute similarity brings to the table. And local Moran is about correlation. Local Geary is about distance. These are two different things. Sometimes they capture similar locations, sometimes they don't. And so if we compare at the 0.05 level, we see some correspondence here in the local Moran and the local Geary picking up low values, but then local Geary picks up these locations in the north as low, and local Moran does not at all. The outlier is not present in local Geary, and there is some little bit of overlap in terms of the high clusters here and in Normandy. But then this is a common negative low-high outlier, but this one is not. So as we crank up the p-values, the correspondence between the two only focuses on the low end in the southeastern part of the country. So my approach to this is not one is better than the other. They both bring information to the table, and in an exploratory sense, we're interested in finding out what are the matches and what are the places where there is no match, and that should help us think about this notion, the trade-off between attribute similarity and geographical similarity. So basically, when you compare them, there are different types of attribute similarity. As I mentioned a couple of times now, Moran's eye is about cross product, Geary C is about distance. They have power against different alternatives. So I haven't spoken about this too much, but the Moran's eye is more of a linear test against linear alternatives, whereas the Geary C is also pretty powerful against nonlinear alternatives, because the notion of distance does not involve any linearity at all. But of course, in practice, I mean, it's all good and well to know that it has more power against certain types of alternatives, but in practice, you have no idea what the true alternative is, so you're out of luck in that sense. So therefore, in my own work, I often use both side by side in order to find, as I mentioned, interesting locations, places that require further attention. Okay, the second type of statistic was developed by Art Getis and Getis-Ord in the early 1990s, kind of around the same time as the LISA statistic. It's not actually a LISA in a strict sense, because there is no connection, proportionality connection between the local and the global, as we've seen with the local Moran, for example, and we can also show is the case for the local Geary. And the logic is a little bit different. So the local Moran and the local Geary were really kind of thought of as in terms of the formal expression of a spatial autocorrelation test as a double sum, and then this one component can be the local part. The GI and GI star statistics that Getis and Ord developed came out of a point pattern analysis logic. And we haven't spoken much about point patterns, but to find clusters in point patterns, a strategy to assess that is to simply count the number of points within a given radius. So this is called density-based clustering. And if that number of points is more than you would expect under randomness, you have a suggestion of clustering. If it's less, then you have a suggestion that the points are more spread out than they would be under spatial randomness. So the GI and GI star statistics are similar, but instead of counting points, they count values in the surrounding locations. So it looks very similar to a local Moran, except there is no XI part in here. So the GI statistic counts the values for X at the neighboring locations. So it's simply an average of the neighboring locations relative to the total sum. And the big difference between the GI statistic and the GI star statistic is that in the denominator, here XI is not included. So for each location, the denominator is slightly different in that the value of location I is not included in the denominator, but it's never included in the numerator, because we know that the weight WII is 0, so XI is never counted. So in this particular case, we take the average of the values in the neighboring locations and divide it by the total sum of the values. It's a very simple statistic. The GI star statistic is the same, except that the denominator, I'll get back to this in a second. Oops. The denominator here. The denominator includes all the XI. So the denominator is actually fixed. So the GI star and GI are mostly the same. There could be small differences when some locations contribute a lot to the denominator, but the GI star statistic is a very easy statistic to compute. You take the average of the neighbors and that's it, right? So let me go back here. The inference, and this is for both, it's the same, same idea as for the local Moran or the local Geary. You make some assumptions, normality, randomization, and then using standard mathematical statistics, you find what the mean or the variance could be, and you use an approximation. Just like with the local Moran, this approximation tends not to be very good. So my preference is to, and also what we implemented in GeoDa, is to use conditional permutation in this case. So same idea, keep the value at I fixed, shuffle the other observations around, and in this case just simply compute the average of the neighbors. So the difference between the local Moran and the GI and GI star statistics in the numerator is that the local Moran actually creates a cross product of the value at I and the average of the neighbors. In the GI statistic, it's only the average of the neighbors. There's no cross product involved. As a result, the GI statistic does not measure negative spatial autocorrelation. I'll get to that in a few minutes. So the maps are very similar. We find significant locations. The positive values, we don't need a Moran scatter plot. The positive values for the GI or the GI star statistic denote clustering of high and high. We call them hotspots. Negative values are cold spots. So only high and low, no spatial outliers in the GI statistic. Okay, as I mentioned, the GI star statistic is basically the same except for the denominator, and the maps are almost always, in my experience, indistinguishable between the two cases. So there might be very slight differences at the margin, but essentially it doesn't matter which one you use. I tend to use the GI star statistic because it's simpler. The denominator is just fixed, so for all practical purposes, you can ignore it. You don't need to take it into account. Okay, how do we interpret this? As I mentioned, no spatial outliers, no negative spatial autocorrelation. As before, in all the other cluster maps, we only focus on the significant values. We select the cutoff point for significance, and then everything else that doesn't meet that, we ignore. So this is a same comment I made earlier in an earlier module for the global spatial autocorrelation statistics. You only characterize them as positive or negative if they are also significant. If they're not significant, then they don't have a sign because in essence they're spatially random. So this is something to keep in mind. In some other software, they give p-values for everything. I don't do this. If it's not significant, it doesn't matter what the sign is, it's irrelevant. So we only show the significant ones. Positive values of these statistics, as I mentioned before, suggest clustering of high values called hotspots. Negative values, clustering of low values or cold spots. So how do they compare to the local Moran? It's really a matter of preference. The GI statistics are very easy to compute. You don't have to do a cross product. On the other hand, they don't capture negative spatial autocorrelation. So one negative spatial autocorrelation is not of interest to you, then the GI statistics or GI star statistics are easy to use. But if you're interested in local spatial outliers, then they simply don't take that into account. Now, in the literature, it's sometimes argued that the Geary, the GI star statistics are easier to interpret because the sign tells you what kind of cluster it is, and the local Moran as such doesn't do that, but once you superimpose it on a Moran scatter plot, then you're back in business. So at the end of the day, it doesn't really matter. They both give information on the type of cluster you have. Now, when you put them side by sides, I think this is an interesting comparison where you see in what's going on here. So this is the Moran, local Moran map that we've seen before with the two spatial outliers. And this is the map obtained by GI star statistic. Basically the same results, the same locations, except this one here is not picked up as high with the GI statistic, but basically everything else is the same, except look at what's going on. This is a low-high outlier in the local Moran. So we saw earlier on the map, this is a kind of a little bit lower value, but this one we saw is particularly high. So in the Getis-Ord statistic, this value is compared, actually this value does not come into play. It's the ratio of the neighbors relative to the total sum. And this ratio of the neighbors in this case is high enough so that it is not picked up as low high, because this value is actually not counted in the GI-star statistic. So it characterizes it as a hotspot, as a high cluster, right? And then here we have the same. This low-high is characterized as high, and then this high-low is characterized as a low. Why? Because the high value in the middle, so you can think of the donut, the middle of the donut is not counted in the GI-star statistic. In contrast, in the local Moran, the middle of the donut is multiplied with the weighted average of the neighbors, and hence we are able to distinguish positive and negative spatial autocorrelation. In the GI-star cluster maps, those spatial outliers tend to be associated with the type of value that's at the neighbors. So even though we know from the local Moran that this value is actually different from its neighbors, it's characterized as a high cluster because the neighbors themselves are high. So that's the main difference between these two. So in a nutshell, now we have three types of local spatial autocorrelation statistics. We have the Moran-Xi, local Moran, with a clear distinction, high, low, low, high, low. We have the local Geary, which is a little harder to interpret because it's based on distance in attribute space, not on a cross product. So if we're lucky, we can use the Moran scatter plot to get some insight into what type of association is associated with positive local spatial autocorrelation, but it doesn't always work. And then the Getis-Ord statistics ignore the value at the core, at the middle of the donut, so they cannot deal with negative spatial autocorrelation or with spatial outliers. So if that doesn't matter, they're very easy to interpret as hotspots and cold spots, but they do not take into account spatial outliers. So these are the tools. Now, the next set of slides will revisit how to interpret this and how to assess significance.